Hi, engineers. Today I want to explain to you Big O notation, so you become more confident during your tech interviews and land to your dream job. Let's learn Big O notation from zero. Today, we'll answer what Big O is, why interviewers care, and how to estimate it fast, even if you're just starting to code. We'll keep it super simple with plain English examples first. Then we'll walk through 3 tiny demo patterns you can use in almost any interview. In the end, we'll recap a few rules of thumb you can say out loud while coding. Let's rephrase Big O in plain English. Big O is a way to talk about how the amount of work grows as the input gets bigger. We don't measure seconds, we count rough steps. If we double the input, do we do the same work, a little more, or a lot more? That's it. Why do interviewers care about it? They want to know if your solution will still be fast when the data grows. And they want to hear you explain trade-offs, the quick and simple way versus the efficient and scalable way. 2 handy principles before we start. First, we focus on the worst-case scenario, unless told otherwise. Second, we ignore constants and little details. We keep only the growth shape. So instead of 3 passes over the list, we say O of n. Now, 5 Big O classes you'll see all the time, with simple pictures. 1. O of 1, constant time. Think of opening a desk drawer that always takes 1 pull. Reading an array value by index is like that. 1 direct step, no matter how big the array is. How to say it in interviews. Time O of 1. Work does not grow with input. 2. O of log n, logarithmic time. Think of finding a word in a paper phone book. You keep having the pages. That's binary search. Every step cuts the space in half, so adding more pages adds only a few extra steps. How to say it. Time O of log n. We have the search each step. 3. O of n, linear time. Think of a conveyor belt with items passing by. You look at each item once. That's a single full scan. Double the items, double the work. How to say it. Time O of n, 1 full pass over the data. 4. O of n log n, sorting time. Think of a sorting funnel that breaks a pile into halves, sorts each half, then merges. Most efficient general-purpose sorts run in O of n log n. If your plan is sort, then do a quick pass. You're usually here. How to say it. Time O of n log n due to the sort. The post-sort scan is linear. 5. O of n squared, quadratic time. Think of a room where everyone shakes hands with everyone else. For each person, you compare with every other person. Classic double loop pattern. How to say it. Time O of n squared. 2 nested loops over the same data. Quick side note. You can mention but don't dwell on. O of 2 to the n and O of n factorial blow up very fast. If you hear try all subsets or try all permutations, you're probably here. In interviews, avoid these unless the input is tiny. How to estimate Big O quickly while you code. 1. Count loops. 1 loop over the data is O of n. A loop inside a loop over the same data is O of n squared. 2. Halving or doubling the step size is O of log n. 3. Sort plus something is usually O of n log n. 4. 2 separate passes are still O of n. We add them and keep the biggest shape. 5. Hash maps and sets usually give O of 1 average time for add, check, and get. 6. Space matters too. If you build a brand new list of size n, that is O of n space. If you keep a few variables, that is O of 1 space. Now, 3 tiny demos you can narrate in any interview without writing heavy code. We'll also say the complexity line right after each one, so it becomes a habit. First, let's create a function named maxInArray that takes 1 input named ARR. We will return the largest number from this list. Inside the function, we create a variable named best and set it to ARR at index 0. This gives us a starting champion to compare against. Next, we start a for loop. We declare I starting at 1, We keep going while I is less than ARR length, and after each round we increase I by 1. This scans the list from left to right, skipping index 0 because best already holds that value. Inside the loop, we create a variable named current and set current to ARR at index I. Then we write in if statement. If current is greater than best, we update best to current. That means we just found a new champion. When the loop finishes, we return best. At this point, best holds the largest value we have seen in the entire list. Complexity, time O of n for one full scan over the data, space O of 1 because we keep only a few variables. Now let's test it quickly. We are writing a console log of max in array with the list 3, 7, 2, 9, 5. When we run the file in the terminal, we should see 9, 2. Binary search on a sorted list. First, let's create a function named binary search that takes two inputs named ARR and target. We will return the index where target appears or -1 if it is not found. Inside the function, we create a variable named left and set it to 0. This points to the start of the list. Next, we create a variable named right and set it to ARR length -1. This points to the last valid index. After that, we start a while loop with the condition left is less than or equal to right. As long as our search window is valid, we keep checking the middle. Inside the loop, we create a variable named mid. We set mid to the floor of left plus right divided by 2. This gives us the middle index of the current window. Next, we write in if statement. If ARR at mid is exactly equal to target, we return mid right away because we found the target. Otherwise, we write another check. If ARR at mid is less than target, that means the target must be to the right of mid, so we move our left pointer forward. We set left to mid +1. If that check is not true, then ARR at mid is larger than the target, so we move our right pointer left. We set right to mid -1. When the while loop finishes, it means the window collapsed and we did not find the target. We return -1. Why this works? Each step cuts the remaining search space in half, so we quickly narrow down to the target or prove it is not there. Complexity, time O of log n because we have the search each step, space O of 1 because we only keep a few variables. Now let's test it quickly. We are writing a console log of binary search with the sorted list 1, 3, 5, 7, 9, and the target 7. We are writing a second console log of binary search with the same list and the target 4. When we run the file in the terminal, we should see 3 for the first one, because 7 is at index 3, and -1 for the second one, because 4 is not in the list. 3. Two-sum, naive versus hash map. Naive version. First, let's create a function named toSumBrute that takes two inputs named nums and target. We will return a pair of indices whose values add up to target, or null if none exists. Inside the function, we start a for loop. We declare I starting at 0. We keep going while I is less than num's length, and after each round we increase I by 1. This picks the first index of a pair. Inside that loop, we start a second for loop. We declare j starting at I plus 1. We keep going while j is less than num's length, and after each round we increase j by 1. This picks the second index that always comes after I, so we do not repeat pairs. Inside the inner loop, we write an if statement. If nums at I plus nums at j is exactly equal to target, we immediately return the pair I and j. If both loops finish without finding a match, we return null. Why this works? We test every possible pair, so if a valid pair exists, we will find it. Complexity, time O of n squared because of the two nested loops, space O of 1. Now, let's create the faster approach that uses a hash map. We create a function named toSumMap that takes the same inputs, nums, and target. Inside the function, we declare a variable named map and set it to an empty object. This will map a value we have seen to its index. Next, we start a single for loop. We declare I starting at 0. We keep going while I is less than num's length, and after each round we increase I by 1. Inside the loop, we create a variable named needed and set needed to target minus nums at I. This is the complement we want to find. Then we write a check. If map already has needed, it means we saw the matching value earlier. We return the stored index from the map together with the current index, I. Otherwise, we store the current value for later. We set map at nums at I to I. If the loop finishes, we return null. Why this works? We trade memory for speed. By remembering what we have seen, we can answer, is the complement here in constant time? Complexity, time O of n on average for a single pass with constant time lookups, space O of n for the map. Now let's test both versions quickly. We are writing a console log of toSumBrute with the list 2, 7, 11, 15, and the target 9. We are writing a console log of toSumMap with the same list and the same target. When we run the file in the terminal, we should see 0 and 1 for both calls, because 2 plus 7 equals 9. Common traps and how to avoid them. 1. Early returns don't change the worst case. If your solution sometimes stops early, still explain the worst input. 2. Hidden heavy steps. Sorting is O of n log, and even if the rest is tiny. A complex regular expression can be expensive. Mention the big step out loud. 3. Building new collections. If you copy or build a result the same size as the input, that is O of n space. If you keep a stack or a map of up to n items, say O of n space. 4. Nested work by accident. A map inside a loop is fine, but a scan inside a loop over the same data might accidentally make O of n squared. How to speak complexity during your solution, line by line. Right after you finish the main idea, say, complexity, time O of n because we scan once, space O of 1 because we keep only a few variables. Or, if you used a map or stack, say, complexity, time O of n for one pass, space O of n in the worst case for the map. If you sorted, say, complexity, time O of n log n due to sort, space depends on the sort and any extra arrays we allocate. Mini checklist you can keep on a sticky note. Do I loop once or nest loops? Do I have the problem each step? Do I sort? Do I build any new arrays, maps, or stacks as large as the input? Can I keep just a few running variables instead? Quick recap. Big O describes how the work grows with input. We keep only the growth shape, not the tiny details. Your 5 core shapes are O of 1, O of log n, O of n, O of n log n, and O of n squared. Learn to spot them with loops, halving, sorting, and nested comparisons. Always mention space, as well as time. And right after you finish coding, drop one sentence. Complexity, time, space. That's it. Now you're 1% smarter. The cheat code is consistency, so keep boosting your brain. Make it your daily routine, and you will nail your next interview. Same rhythm tomorrow at Code Crack Interviews.